Hello, this is 641 it's actually called model-based image processing, and today is Monday, September 30th, and our lecture today is going to be on non-Gaussian models for images. So is the lab due this week? Is a lab due this week? How's that coming along? I see a lot of people kind of looking down and moaning. Maybe we want to try to go over that a little bit, but for the lab you just have to do the quadratic case, right? Because we're just doing the first half of the lab, correct? So it's just mainly implementing that update equation in the previous thing, recursively. You update a pixel, you update a pixel, you update a pixel, right? And that's coordinate descent. So you should be able to do that. One thing, here's a debugging trick. Compute the cost function you're minimizing. So write a subroutine that evaluates the cost function, okay? Now, one thing you have to be a little careful about when you evaluate the cost function is you have to make sure the cost function is computed exactly correctly, even on the boundaries. The boundaries are where things get screwed up, because what happens is that, so we've had all these equations and everything, and it's all good, but most of it you're just nodding. And now you're going oh yeah, it's all great, I understand everything, right. Then you have to go do it. And you're like, I don't understand. The funny bone is connected to the what bone? Okay? And you have no idea how the thing, it's like, oh my God, I don't know what to do. So of course, the first thing you do is panic. Then you go to the notes and you go, oh, wait, hold on. I know he said something about connecting a whatchamacallit to a something or other, okay? And then you try to implement something, right? That's where the rubber hits the road. When when you can do that, then you actually have some idea what you're doing, okay? Now the point is this, what's your cost function? Your cost function, I think for the first case, it's just f of x. So this is the lab, part 1. F of x is 1/2 sigma squared or something like that. The norm of y minus x. So there's no forward model. Well, there's the forward model is the identity, okay? And then plus, there's this prior thing, right? So what's the prior thing? The prior thing is you're taking the sum over pairs of pixels. So this is pairs, okay? And then you're taking 1/2 sigma x squared. And then there's a BSR. It's actually BS minus R. And then there's an XS minus XR squared. Okay? And you're trying to minimize this thing, right? You're trying to minimize it. Right? Is that the goal? And what does this thing do? Why do you want to minimize this part? Where does this part come from? What the heck does it mean? So what's the model? The model here, underlying model, is y is equal to x plus w. Pretty simple model. X is the image you're trying to recover, right? Y is your observations. What's W? It's Gaussian white noise, right? And what's this variance? Yes, but it's this thing here, right? I could put a W if you want, okay? Where does this expression come from? Where did it come from? Why did I write this down? Yeah, well, close, but not exactly correct. There's just a word missing, okay? Well, okay, so this thing here is what? It's the, you said it's the likelihood, right? Okay, and that's almost true. So what would the likelihood be? It's the log of the probability distribution of y given x, okay? Except for that's not quite true. In fact, it's completely wrong. If your answer is almost exactly right but completely wrong, what does that mean?
Negative sign?
Yeah, you forgot a sign, okay? So as this quantity gets smaller, that gets more probable, okay? So you have to have a negative sign, right? So we want an x which makes the y likely, okay? We use the word likely when we talk about this function as a function of x, and we use the word probable when we call it as a function of y. It's sort of a subtle distinction. The function of x is the likelihood. The function of y is the probability. Okay? Does everybody remember this? So this is normally called least squares, right? You're minimizing square error. But the interpretation is more sophisticated interpretation is that it's the negative log probability, right? Why do you want to make this term small? Intuitively? I just want to make sure everybody's here, especially since it's Monday.
The data you're getting is matching what?
Yeah, your observations match your guess. Your reconstruction matches your observations. If we only cared about that term, what would the answer be? Y. So that would be kind of disappointing, right? That we'd be like, you're telling me I took 3 credits, I had to show up for all these classes, I had to do all these homework problems, and you're just not going to do anything? I mean, I don't feel like I'm getting much for my money, okay? I just take the y and x is y. It's pretty boring. But what's that solution called? Excuse me? That's the maximum likelihood solution. It has the interpretation of being, of course, in another context, people would call it least squares. In a probability framework, you call it the maximum likelihood. It's the same, different names for the same things, but it's the same thing, but it's just a different interpretation. So is the maximum likelihood answer good?
Depends on how bad your white noise is.
It depends on how bad your white noise is. So let's say your white noise is really bad.
That's really bad.
You'd want to try to do something better, right? By the way, has anybody ever heard of a thing called denoising? Huh? Do you know what denoising is? It's a method, these are popular methods for taking images and removing noise, right? So if the maximum likelihood estimate was good, there would be no denoising algorithms. They would be unnecessary, or they would be useless. But are denoising algorithms useless? No, they're actually impressive. They do like amazingly good jobs sometimes, okay? So why does the denoising algorithm work? As opposed to just saying, I'm sorry, this is the noise. It's too bad. That's the best I can do. Why does denoising work?
Because of priors?
Because of the prior. If you didn't know, let's say your image was literally white noise. Let's say your image was white noise. You just took independent Gaussian random variables, say with some non-zero mean so that the image doesn't go negative, okay? Or doesn't go, then let's say your image was white noise, and then you added white noise to it. If this is white noise and you add white noise, can you denoise it? how could you separate white noise from white noise? They look identical. The reason you can process signals to make them better is because this is like source separation. You have, if this and this are exactly identical, okay? They have the same, not identical in the sense they're not equal, but in the sense that their distributions are the same. See, that's another key issue that people don't understand. It's a good thing that they don't understand it, because you can use that knowledge to make money, okay, or to get a job or something, okay? Well, maybe it's not a good thing, but given that it's true, you may as well be the person who understands it, okay? So what people don't understand is they don't understand probability. So when I say they don't know what I mean when I say, well, if I say they're equal, they say, well, they're equal. And I go, no, they're not equal. They have the same distribution. People get very confused about that, because the idea that they can't distinguish between a random variable, which is unknown, and an actual value, which is known, right? But you guys understand that. You understand that something can have a probability distribution. It can be a random variable, right? So if the distribution of this and this are the same, how could you possibly separate them? I mean, you have white noise and you add white noise to it. So you have to then separate. It's as if you have, you have dollars in a bank account, and you can't separate they say the money is fungible, okay? If I put $1 in, I put another dollar in, the bank account, they can't tell the difference between the $2. They're just $2, right? So if these are the same distribution, I can't separate them. In that case, the maximum likelihood estimate, it's the only thing I can do, right? But if the distribution of these two things is different, then I could use that information to somehow take them apart, okay? Now, the distribution of W we're assuming here is white noise. But is it image white noise? No, image is not white noise. Images are not, there's some probability that you generate white noise and it looks like a picture of your Uncle Bob fishing, okay? But it's very low probability, because in the space of images, images live in a space. If there's n pixels, they live in an n-dimensional space, right? If I put a random point in that space, that would be like picking white noise. The probability that that's going to look like an image is excruciatingly small. It's basically 0. It's not quite 0. It's like 10 to the minus some ridiculous number, like 10 to the minus a million, okay? So the probability that it's going to look like an image is ridiculously small. So what does that mean? That means most of the space is empty. The image lives in a very small subset of the space. So that means its probability distribution. One way of embodying that idea is that the probability distribution, right, is concentrated in a very sparse subset of the full space. I can use that information to separate these things, to tease them apart. Okay? So this is my prior distribution. So what am I saying here? I'm saying that this quantity, this is a sum. It's summing over neighboring pixels. So I have pixels in an image. I just want to go over this. The reason is that what I really hate is for you to come out of this class, get an A+, and have absolutely no idea what you did, okay? So I want you to have an understanding. It's better that you come out with just a basic understanding, because you can always figure out all the complicated details later, okay? So what we're doing is we're summing over pairs of pixels, say neighbors. So let's say 4 the nearest neighbors. So we're only summing over pairs of pixels like this, right? So this is the sum over all pairs of neighboring pixels, okay? And for each pair of neighboring pixels, we take the difference between the two pixels. This is xs, this is xr. And we take xs minus xr, and we square it, okay? Now, would you expect that quantity to be large or small?
Depends on where we are in the image.
It depends on where you're in the image. Let's say a typical image in a typical location.
Small.
You kind of expect it to be small. Why?
Expect nearby pixels to be similar.
You would expect nearby pixels to be similar. Is that always true? No. Why? Because you can have an edge or something, right? Edges occur a lot in images, right? So what is this probability distribution saying? This is the negative log. This is the negative log. If the negative log is large, what does that tell you about the probability? Maybe logs are less intuitive. Everybody, I think, is more intuitive about exponentials. So the other way of it, so you have u of x is equal to, say, 1 over 2 sigma x squared. I'm just rewriting that thing. SR. This is a member of the pairs. And then we have B S minus R. The B's are always positive. They don't really have to be, but let's assume they're always positive. XS minus XR squared, okay? So that's U. So then the probability distribution, P of x, is equal to the exponential of minus U, okay? And this is Z. Alessandro, does this look familiar?
Yes.
Why does it look familiar?
It's the commodity equation.
Yeah, but it's also, from your material science background, you must see things like this all the time, right? What is it called? Do you remember?
Gibbs.
It's the Gibbs distribution. It's also known as the Boltzmann distribution. It's really not that it's really not a very strong assumption, because as long as the probability density function isn't 0, I can always represent it this way, right? Because I could just take the log, okay? As u gets large, what happens to the probability? It goes down. This is, in thermodynamics, this is called the energy. This thing is the probability, okay? So if the energy goes up, the probability of the state goes down, because it's harder to get the higher energy states. So higher energy, lower probability. Larger U, smaller P, right? Okay, this thing is U. Okay, that thing's U. So if the difference between the pixels gets larger, what happens to the probability? It gets smaller. Is everybody with me on this? If you have the least bit of fuzziness or concern or whatever, ask a question now, because it's these simple ideas that are most important, okay? So as these pixels get further apart, the probability goes down. So that means it's more likely that pixels are close. So this is a probability distribution on the space of all images, okay? Is this a very good probability distribution? I would say no, okay? I mean, I guess good is a subjective term, so you're all welcome to have your own opinion. But if I generate a sample from this distribution, would I expect it to look like Uncle Bob fishing? No. Or, excuse me?
It would look very blurry.
It would just look like, first of all, it's Gaussian, right? If the B's are invariant to position, it's homogeneous, which means it's stationary. Homogeneous means the model's invariant to position. If this was circulant, okay, we have a circulant boundary, then it's shift invariant. The distribution is shift invariant by symmetry, okay? So it's got to be, it's a space invariant Gaussian random process. All space invariant Gaussian random processes are reversible. So basically, this has to look like filtered white noise, because you can generate any Gaussian random process by any stationary Gaussian random process by just filtering white noise, okay? You just filter whatever the desired power spectrum. You just filter it to achieve the desired power spectrum. So you calculate the power spectrum of this. By the way, the power spectrum of this is going to be related to the Fourier transform of those. Okay, and then that's what, do you think filtered Gaussian white noise is going to look like real images? No, not unless your application is that you're looking at filtered Gaussian white noise. I mean, but it's not, is it going to look like a CT scan? No. Is it going to look like, you know, Aunt Margaret? No. Is it going to look like, I don't know, some famous movie star that I'm unaware of because I'm really not very up on pop culture? No. Is it, it's just not going to look like an image, right? So this is what I call a bizarrely simplistic prior, or a BSP. It's a bizarrely simplistic prior, okay? It's stupidly simple, okay? Here's the thing, it's better than nothing, okay? But is it good? No, okay? It's really silly. It's a silly, really simple prior, okay? It's basically just saying your image is band limited, is essentially what it's saying. But it's still better than nothing, okay? So what's going to end up happening is the images that come out of here are not going to really be very close to the images, the real images, but,
So does the prior model more say things about the neighborhood more so than the image in general?
Well, it shouldn't just say things about the neighborhood, because clearly images are more complex than that, right? Like, for example, if I like to always give the example that, well, I'm just trying to think. If, I mean, images clearly have long range dependencies, right? If I have a picture of the classroom, and these are the chairs. Oh, it's going to take me. And then I take out this region here. I cut it out, and I say, what do you think's in there? Well, you think the chairs are probably going to be in there, because you see it's a classroom. There's long-range context. In fact, there's these algorithms called what do they call them? It's a very common name. I'm sure you've heard of it. I can't remember what they're called. They're called in-painting. In-painting. You've heard of in-painting? Have you heard of in-painting? So you can cut out a big chunk of an image and just fill it in, okay? And it'll fill it in with something that's plausible, okay? Now, if it's an if it's humans will do the algorithms will do a great job in terms of creating like individual pixels that seem reasonable, but the overall context may be weird, okay? Like it's sort of like, have you heard of these things, GANs, that produce random? Okay, everybody's heard of them, right? And the thing's called deep fakes. Like they talk about deep fakes. It's all the same kind of thing. So the algorithms won't know high-level human sorts of things often, although they're getting better and better, so that maybe there'll be things here that don't make any sense, okay? But the point is there's long-range dependencies. But in this bizarrely simplistic prior, we're just trying to model the very, very simple local interdependencies for two reasons. One, it's computationally more tractable, And 2 is that it's someplace to start, okay? In the class, we'll eventually talk about more and more sophisticated models, okay? But we have to start somewhere. So now what we want to do is we want to minimize this function because the minimum of this function is the map estimate. And the map estimate has the interpretation, if we did the maximum likelihood, we wouldn't really be able to do anything. But here we say, okay, well, we try to fit the data, but we also try to make it fit the model for the image. We want to balance those two things. So now, so is everybody good with that? So now we're going to try to minimize this function. There's a lot of ways we could do it. We could use gradient descent. We could use conjugate gradient. But I think for the lab, you're supposed to do coordinate descent, okay? So in coordinate descent, what happens is you have f of x1 through xn. And then over here, this is xk, say. You take the kth entry, and you just minimize with respect to that one entry, okay? You pick the one pixel to be the best choice for given all the information, okay? So you minimize this function with respect to that one pixel. Then you go to the next pixel in some order. You can pick any order you want. Sometimes people pick random order. Actually, random order is a good way of doing it. But you could do raster order, that's fine too. And if you go to optimize the same pixel, nothing will change because you already had the best value, right? But if you go to some other pixel, you update it. You update it with the goal of minimizing this function, okay? Then once you get to every pixel and you minimize the function with respect to every pixel, you start all over again. Now you might say, well, why am I starting again? Because I already minimized with respect to those pixels. But you changed all the other pixels. So the solution is interdependent. You're no longer at the minimum of that pixel, right? Okay. If you're looking at it in the diagrams, in the book, it looks like this. You have some function. Say the function looks like this, like that, right? So the idea is that this is pixel 1, we'll call it x1. This is pixel 2, we'll call it x2. So you start at some point here, say, okay? And then, or I guess I could start at 0. Okay, well, I'll start here. Then we go along this direction, x1, until we get to a minimum. Say the minimum's there, okay? Then we pick x2 and we go like this to here, okay? And then we go like this. So what you're going to do is like this. Hopefully, you eventually get to the minimum, okay? But it's not so direct in some sense. All right? But each of those updates is really fast. The alternative in gradient descent is you start at some point like this. The gradient is this way. So you do a minimum, you go to here, okay? Now, it looks like maybe that would converge really fast, but actually it tends to run into problems that we described, okay? Because what ends up happening is that the gradient descent, yeah, there are issues. What'll end up happening is it'll kind of go like this a lot, and it could be slow convergence. Okay? But we're going to use coordinate descent, right? So you understand what coordinate descent is. You understand conceptually what gradient descent is, okay? Now the coordinate descent, the update equation, is simple. Hold on. I feel like I'm going to show it to you. Okay. This is one of those times where it's important to remember what you're doing. So this is the update equation. Oh, that's the update equation, but here's that's the fast update. It does the computation in 2 steps. Here is the slow update. So this is the update equation. So what's this? First, y minus ax. What x is your current guess at what the solution is, okay? Ax is, if that guess is correct, A would be the measurements you would expect to see. If you subtract it from y, that's the difference between what you expected to see and what you did see. Then that's a vector. You multiply it by the sth row of A. Why do you do that? Because if you change A, if you change the pixel to location S, okay, A star S is the perturbation that you would get in the measurement given that you change that one pixel. Do people see that? No. Maybe. Not really. Okay? Let me explain that, because that's an important thing. So, what happens is this. So you have y equals ax, right? That's sort of the forward model. And that means that y looks like a vector like this. Then A is a matrix, right? And x is a vector, right? Now, if this is the pixel xs, right? It's right there someplace, okay? So when I multiply xs times A, this kind of comes over here, and this is the position S. That's the sth position, right? So it modulates that column, okay? Which then it gets accumulated to the output. So this thing here is what I'm calling A star S, okay? Does that help? Now, here's the thing you have to be careful about. You almost never, what you guys might go and do in your zeal to complete the lab is you might go into MATLAB or whatever and try to actually store this matrix A. Bad idea. This is just a concept, okay? It's a concept mathematically, it's beautiful, but it's not a good way to program it because A is huge. So conceptually, you're going to have this vector, but in physical, on the computer, most of the entries are usually 0. So you don't want to have to evaluate the entries that are 0, because that's just a waste of time, right? So let's come back. Did I answer your question? Does that help? Or do you have more questions? So what's going on here? Oh, laptop. Okay, so this is the 8th column. It has the same dimension as the output. So you take the inner product between those two things. Okay, and then, so this is a scalar then. And then this is also scalar. It's the difference between what you would have predicted at a point in the image, given your, it's like, okay, so your pixels should be, you would expect your pixel to be similar to its neighbors. So this is the difference between the pixel, and this is usually like an average of the neighbors, because the G function usually sums to 1. In other words, when you go to do the prediction, your weights usually sum to 1. Okay? And then you do this other junk here, and then you get that, okay? Do you understand? So you have to implement this in the code. But that's not so bad. Especially because A, in the case where, in the denoising case, A is just the identity matrix, so there's just one non-zero entry per column anyway. Right, so that's pretty easy. All right? Now, the thing though is that there's a computation that speeds this up, which is that you keep an error vector. Rather than have to keep recomputing the error vector, the difference, but E there is the difference between the measurements and what Y are the measurements, right? AX is what you would expect the measurements to be if X was the correct solution. Iterative reconstruct, so all these algorithms, map estimation, this is about recursive trial and error, okay? Basically, I like to say it's like my wife asked me to go to the supermarket to get some stuff. I go to the supermarket. The first try, I usually bring back everything is all wrong, okay? I got the wrong fruits. The thing was, there was the wrong brand, okay? So she explains, okay, you did this wrong, you did this wrong, you did this wrong. I go back and I correct the errors. But I still correct them all. So then I come back and she goes, okay, that's better. 3 of the 5 things are correct. And then she makes corrections on the other things. And I repeat. It's like, what do they call it? Wash, rinse, repeat. Wash, rinse, repeat, right? So you just keep, you're searching for the solution to this problem. You just keep going back and adjusting it. It's trying to get closer and closer, right? So you keep, E is your error. You'd like that to be small. Now, are you looking for the solution that minimizes the norm of E? No, because that would be the maximum likelihood estimate. And the maximum likelihood estimate isn't good because it doesn't account for the fact that the image also has to be reasonable, okay? So that's why you have 2 terms here. You have E, this term, and you have this term. This is the forward model, that's the prior. You do the update of X, and then when you change X, E has to change correspondingly. So you make this update. This algorithm is faster, okay? Because it doesn't have to, it keeps sort of 2 states, one for the image and one for the sinogram, or one for the measurements and one for the image. And it keeps them sort of the same, okay? So rather than having to recompute every time, okay? So does this help at all for the lab? Okay, you very kindly nodded. I hope that there's some use, okay? Any questions then? Any questions? Okay, now the problem is this, that the problem is this. Okay, so this is all good, and if this truly was the distribution in the image, then this would be the map estimate. But this isn't the distribution of an image. Why? Because images don't look like this at all. Okay, real images don't look like this. First of all, Gaussian distributions, Gaussian random fields. So this is a stationary Gaussian random field. So it's just going to look like filtered white noise. My friend used to always call this a dirty handkerchief. It kind of looks like a dirty handkerchief. Okay. Try generating Gaussian white noise and filtering it with a low-pass filter. It doesn't look like a regular image. So one reason is it has no edges in it. It's smooth, right? So we're not going to fix everything, but at least we can incorporate edges. Okay. So how do we incorporate edges? Now, what happens is this. This key issue. We have this function, rho of delta equals 1/2 delta squared, okay? And then, so the function there is xs minus xr squared is equal to rho, I'll put a 1/2 here. It's chalk dust, believe me. Okay, all right? So when this gets large, what happens to the probability of the image?
Decreases.
It decreases, okay? Because you're saying that images pixels that are nearby each other should be similar in value, right? But sometimes you have edges. So Gaussian says that if we took the differences between pixels, this is sort of presuming that the differences between pixels are Gaussian, okay? But in fact, that's not the case because edges create outliers. Maybe there's a few pixels that have very large errors, okay? If you actually take real natural images and you look at histogram, the differences between pixels, you'll get distributions that look much more like this, okay? Typically, this is like bi-exponential, so it'll look like e to the minus delta. Instead of, this looks like e to the minus delta squared. So e to the minus delta squared drops off much faster than e to the minus delta because you're exponentiating. Obviously, x squared grows faster than x. But when you take e to the minus x squared, it drops off much faster than e to the minus x, okay? This is Laplacian. So through, I would say, the 90s, the 80s and the 90s, there was a lot of interest in trying to pick these functions so that you could get good models of images. Of course, this is a hopeless task, okay? Because how are you going to just pick some silly function like this and suddenly get pictures of Uncle Bob fishing? It's not going to happen. But that said, hope burns eternal. And, you know, if you can make things a little bit better, you can get funding from the government and keep being employed, okay? So they keep flogging away at it, okay? So they say, well, how would I pick a better choice? Right now I'm picking this delta squared. How would I pick something better than delta squared, okay? So let's think about that. So this is rho of delta. This is called the potential function. And the reason it's called the potential function is, remember, this overall thing is the energy, okay, in a thermodynamic sense. And this is analogous to thermodynamics, if you've ever taken thermodynamics. This is the energy. E to the minus u of x is the probability distribution. This is called the Gibbs distribution or a Boltzmann distribution, which is the distribution that things have when they're in thermodynamic equilibrium, okay? So this comes up a lot in like solid state physics or material science or any kind of system that's in thermodynamic equilibrium, or in you know, like gases in cylinders, things like that. Okay, so now this, though, is the potential. So what ends up happening is, the way to think about it is you have like an image like this, and the overall energy of the image, of course the image doesn't really have an energy, but it's analogous. The energy of the image is the sum of the potential between neighboring things. This is, we'll talk later about a thing called an Ising model, which was like the classic model that came out of the study of physics in World War II. I'm trying to model the behaviors of materials where you have atoms next to each other that interact. So the idea is only nearest neighbor atoms interact, and then they exhibit certain behaviors. So this is the potential function, and then there's another thing called the influence function, which is just a derivative of the potential function. Rho prime of delta. So this is the influence. The interpretation of the influence function is it's the force that a nearby pixel applies to another pixel. It's how much influence it has on it. The reason is that the potential is energy, right? And the derivative of energy with position is force, okay? Because force times distance is energy, right? So if I differentiate this tells me the amount of force. So it's the restoring force. So it's how much, so generally the force will be applied to force pixels to be equal. Because the pixels, you want them to, you prefer, all things being equal, you'd rather the pixels be near in value, okay? So this is the restoring force that causes, it's like a spring that's pulling the two pixels together. So over here, if I have 1/2 delta squared, that's quadratic, okay? So that's the potential function. And if I differentiate that, that's the force. What's the derivative of a quadratic, right? This is rho prime of delta equals delta, right? This is rho of delta equals 1/2 delta squared, right? So this is like this. So this is telling you if I move this pixel away, it increases the force, the restoring force, linearly, okay? So it's like a spring. The 2 pixels are attached by a spring. The problem is the spring has it has 0 length, so the analogy kind of breaks down in that sense. So as I pull, there's some rest position of the spring. As I pull in the spring, the restoring force increases proportionately to the deflection of the spring. If it's a linear spring, okay, which is what the model is here, okay. Now the problem is this. What ends up happening is that as the pixels become further and further, the restoring force becomes larger, 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 larger. And what it's saying is that the probability of having a really large edge is really small, okay? Too small, because it actually does occur at a pretty high frequency. So instead what you can do is you can say, well, look, I'll have this go up, but if the energy exceeds, if the distance exceeds some threshold, I'll say, hey, it must be an edge. And I'll just let I'll let that be constant, right? So in that case, the derivative looks like this. Oh, shoot. It looks like this. This is t, and it goes like this. All right? So this is the so-called broken spring model. The broken spring model means that you pull the spring until a certain point, and then all of a sudden the spring snaps. Snap. And when it snaps, it stops pulling at all. So there's no restoring force. Now the problem with the analogy of the broken spring is that our broken springs like self-repair, okay? So you pull them to a certain point and then they break. It's as if you have like some kind of crazy magnet contraption that once you pull it, the force becomes too large, the magnet separates, but the springs remain in their extended position. And then when you go back, they re-engage, okay, or something, okay? I don't know. You could come up with some kind of thing, but it would be complicated. But the idea is that at least I'm pulling it out, it breaks, and then the restoring force becomes 0. The problem is that this is a non-convex function, so it leads to, it makes optimization difficult. It's also not continuous. The fact that it's non-convex means that the solutions are not continuous. What's going to happen is that you get discontinuities in your solution, okay, which could lead to like weird artifacts. In the modern techniques are almost all convex functions. It's interesting. When I first started doing this stuff, I was like, I don't know, what do you call it when people, like, when you're a pariah? I guess you call it being a pariah. I was a pariah in the technical community because I had the nerve to suggest using convex functions, okay? And so what happened is that you can use, like, the most common convex function is, shoot. Okay, I don't have time to redraw that. Okay, so, I'm sorry. That's the absolute value function. And this thing then, if the absolute value, the derivative is like this and like that. It's like a sine function. I didn't draw it too well, okay? This is sine of delta. This thing is called total variation. It's pretty commonly used, total variation, because it penalizes the absolute value of the differences between the pixels. This is sort of the most extreme convex function, okay? The problem with it, I'm out of time, but I'm going to let you read you're going to read the notes, correct? Okay. The problem with this is that it tends to lead to images which are, people will typically, if you're processing images like from medical applications, or you want people to use the images like as natural images or something, people will describe these images as waxy. They'll say they look waxy, okay, or plasticky. because it eliminates all the fine detail. If it's like a scientific application where you're trying to segment things into different regions, it could be pretty good. But for a lot of natural image processing, people don't like it because it's waxy, okay? So then that leads to the last possibility, which is that you have something which is quadratic and then linear, okay? In which case, the derivative looks like this, the influence function. This is like a good general choice. The disadvantage of this is that you have to pick a threshold t. With total variation, you don't have to pick any threshold t. Okay. And this is the so-called Huber function. Are you guys reading the notes? Make sure you read the notes. I don't know if I mentioned this before, but it's important to read the notes, okay? Okay, so you're going to read about this. Now the problem is multifold. First of all, you have to pick one of these functions, and then you have to pick the parameters of the functions for your application. And you'll do that for the second part of the lab. But the second thing you have to do is you have to figure out how to do optimization. Because now it's not a quadratic function. There's no closed form solution. Before there was a closed form solution, you just couldn't compute it. But now there's no closed form solution, so you really have to do it as an optimization problem. You can use gradient descent. You can coordinate descent. We'll talk about how to do the coordinate descent. The problem is now the rooting, you can't, when you go to do the line search, you can't compute the solution to the line search in closed form. So you have to do it numerically. And some methods for doing it numerically are much faster than others. So we'll talk about that. And that's the section on surrogate functions and majorization, which is a kind of a general technique for doing optimization of non-quadratic functions that are, where you have to do it fast, okay? And that's pretty, okay, and then, yeah. So I think that's pretty much a good breaking point. We'll cover this some more next time. Actually, I think maybe I'll talk a little bit about total variation. Oh, scaling parameters. I think we're pretty much done chapter 6. So you've got to read it, okay? By the way, here is my advice. Read it fast, okay? And if you don't understand everything, fine. Then go back and read it again. It's better to take a couple passes and maybe read it fast before class. I'm going to start chapter 7. So start reading 7 before class. I think most of it, I'd like to believe you can read pretty quickly. It's just that the equations and everything get dense. But the prose, just read the prose and try to roughly understand it. Read it fast, okay? I give you absolution from whatever, okay? You can just read it quickly, okay? And not understand it. It's okay. Then come and I'll talk about it, and then read it again more carefully, okay? Because I think that helps, all right? All right, good. Thank you.